You know, it's funny to think about what a falling apple and a subatomic particle could possibly have in common. I mean, they seem like they belong to completely different universes, right? Governed by totally separate rules. But what if I told you there's a hidden language, this unseen mathematical engine that connects them both? Well, let's dive into the incredible story of how physics actually found it. So, our journey has to start here, with the absolute bedrock of mechanics, Isaac Newton. His first law is just, it's powerful and it's intuitive. It perfectly describes how stuff moves when nothing's getting in the way. Just straight lines, constant speed. It's basically the physics of wide open spaces.
But the real world is almost never that simple, is it? I mean, things are constantly being guided, restricted, forced down certain paths. A planet can't just zip off in a straight line. It's locked in orbit by gravity. A bead on a wire, it has no choice but to follow the wire's curve. And this is where Newton's whole force-based way of looking at things starts to get messy, like really, really messy.
Yeah, the official term for these things is a constraint. It's any rule that limits how a system can move. Now, if you wanted to solve that bead on a wire problem using Newton's laws, you'd have to calculate gravity, sure, but you'd also have to figure out the incredibly complex forces of constraint, the exact push and pull the wire exerts on the bead at every single nanosecond to keep it on track. Honestly, it's a mathematical nightmare. Okay, so this slide basically shows a fork in the road for physics. On one side, you've got the old Newtonian way, rustling with all these force vectors. But on the other, this totally new way of thinking popped up, called analytical mechanics. And its big idea was just brilliant. It was, forget about those constraint forces, just ignore them. Instead, let's reframe the entire problem using something much, much simpler, energy. And this new approach gave us a whole new language to talk about motion. The first person to really lay it all out was the mathematician Joseph-Louis Lagrange. See, instead of juggling a bunch of forces, Lagrange figured out you could describe the entire state of a system with just a single number, a scalar quantity he called the Lagrangian, or L. And the formula for it is just shockingly simple. It's the kinetic energy of the system, T, minus its potential energy, V. That's it. This one little value holds all the information you need to predict the system's entire future path. And this is why it was such a game changer. The Lagrangian approach just works. It doesn't care what coordinate system you use. It just automatically bakes in all those messy constraint forces without you ever having to solve for them. And maybe the coolest part of all is what it tells us about the universe. It says that out of all the zillions of possible paths an object could take, it will always choose the one that minimizes a special quantity called action. It turns out nature is incredibly, fundamentally efficient. So, the Lagrangian was a huge leap forward, no question. It was elegant, it was powerful, but physics wasn't done. Turns out, even hiding inside this beautiful new idea was an even deeper, more profound structure that was just waiting to be discovered. And this brings us to the next hero of our story, William Rowan Hamilton. He took what Lagrange did and uncovered this absolutely breathtaking symmetry at the very heart of how the universe works. You know, as Oliver Johns puts it, moving to Hamilton's view wasn't just about finding another way to get the right answer. It was about building a better foundation for all the physics that was yet to come. And the absolute key to that foundation was its symmetry. Now, Hamilton's big idea centers on a quantity called the Hamiltonian, or H, and this is even easier to grasp than the Lagrangian. It's just the total energy of the system, kinetic plus potential. That's it. It's a concept we're all familiar with. The conservation of energy. But the magic is in what he did with it. Hamilton's stroke of genius was to change the fundamental variables he was working with. Instead of looking at a system's position and its velocity, he looked at its position and its momentum. And here's the kicker. He treated them as equal partners, these independent, symmetric coordinates in a new kind of abstract space that we now call phase space. And just look at what happens when you do that. On the left, you've got Lagrange's equation. It's powerful for sure, but it's one big, kind of clunky second-order differential equation. Now look at the right. Hamilton's equations. You get two beautifully simple first-order equations. One tells you how position changes based on momentum. The other tells you how momentum changes based on position. They're a perfect mirror image of each other. This is the kind of elegance that just makes physicists' hearts sing. So for nearly 100 years, this was just seen as a really beautiful, clever way to do classical mechanics.
a more elegant tool for figuring out the paths of planets and pendulums. Nobody had any idea that it was actually a key, just waiting for a lock to a reality no one could have even imagined.
The thing is, the Hamiltonian formulation was so perfect, so deeply fundamental in its structure, that its true importance wouldn't become clear until the entire world of physics was turned upside down by the quantum revolution. And this, right here, is where our story goes from interesting to absolutely mind-blowing. The math that was developed to describe the orbits of planets turned out to be the exact language needed to describe what's going on inside an atom. Okay, so let's start with the classical Hamiltonian for just one little particle. It's exactly what you'd expect. H, the total energy, is just its kinetic energy, that's momentum squared over twice the mass, plus its potential energy, U. Simple, classical, nothing weird going on here. Then, in the early 20th century, the pioneers of quantum mechanics discovered this strange but incredibly powerful recipe. They asked, what if? What if we just replaced the classical ideas of energy and momentum with mathematical operators? Now, an operator is just an instruction to do something to an equation. So they tried swapping H for the operator that says, see how this thing changes over time, and P for the operator that says, see how this thing changes across space. So what happens? What happens when you take that simple, classical Hamiltonian we just looked at, and you just plug in these weird new quantum operators? You get this, the Schrödinger equation. Now don't get hung up on the symbols here. The absolutely critical thing to see is the structure. This is the fundamental equation that governs the entire quantum world. And the form of the classical Hamiltonian, that p squared term and that u term, it maps perfectly onto the structure of this master equation. It was a perfect fit. And this just wasn't some wild coincidence. That beautiful, symmetric language that Hamilton had created to describe planets and cannonballs was the very same language the universe was already using to write the rules for electrons and photons. The blueprint for quantum mechanics was hidden inside classical mechanics the whole time. Which, of course, leaves you with a pretty fascinating question, doesn't it? Physics is always developing new, more abstract, more elegant math to describe the universe. So if the elegant math of the 1800s held the key to the quantum revolution, what incredible new understanding of reality is just lying there, dormant, waiting to be unlocked by the mathematics we're using right now?